Okay. So we've talked about the intermolecular attractions, and in general, you should have a sense of how strong they are. But now we're going to talk about how they apply. And so we're going to be talking about things like melting points and boiling points. So, first, in general, the stronger the intermolecular attraction, the higher the melting point or boiling point is going to be. This is a direct relationship, right? So, going back to the intermolecular attractions when we first taught them, we loosely ranked these, right? So we said, okay, so there's London dispersion forces. All right, but then we said that dipole forces were stronger than those, but kind of depends on size. So this is assuming everything's about the same size. Then hydrogen bonding, right? And then the thing is, we have ionic and we have molecular, or metallic, sorry. And these, some ionic are stronger than metallic, some metallic are stronger than ionic, so there's no clear-cut winner there. So those two flip-flop all the time. But definitely the strongest attractions are the network covalent. Okay, so again, this is a loose ranking. There are going to be times when dispersion forces are stronger than dipole-dipole, but that's because the molecule might have more electrons, and therefore that's why it might have more dispersion forces than dipole-dipole. All right? So we take this on a case-by-case basis. The first thing is, anytime you need to compare, you should first figure out what type of intermolecular attractions each substance has, then decide which is stronger. So, example. Here we have carbon dioxide, and here we have beryllium dichloride. So, in order to answer which one of these has a higher boiling point, you got to figure out which intermolecular attraction it has, and in order to figure out which intermolecular attraction, you should know something about its geometry and whether it's polar or not. So, if we drew these out, carbon dioxide, I would first start with this Lewis diagram. So we have 16 electrons with carbon dioxide, and with beryllium, which has 2 plus 2 times 7. So these both have a 16. So carbon dioxide ends up looking like this. All right, it's linear. The fact that it has the same electronegative element on both sides means this is nonpolar, which means dispersion forces. Beryllium chloride, the thing about beryllium, and I mentioned this back when we were first drawing Lewis diagrams, is you have to remember beryllium will only make 2 bonds, and therefore beryllium does not need to meet the octet rule, and that's why it's straight. That's why there's no lone pairs. Beryllium can only hang on to 4 electrons, hence 2 bonds. So this is also linear, and it's also nonpolar, which means it also has dispersion forces. So both of these molecules only have dispersion forces. So now we need to decide, well, what makes two things with dispersion forces different? The answer is the number of electrons. Right? So we add up the electrons. For CO2, oxygen has 8 electrons, so times 2 is 16. Carbon has 6, so it's 22 electrons. And again, I'm talking about total electrons, not valence electrons, total, which means you're adding up the atomic numbers. Beryllium chloride, so chlorine has 17 each. 17 times 2 is 34, plus the 4, so 36. Okay, so well, this is not really close. Beryllium dichloride has way more dispersion forces than carbon dioxide does. All right, so the higher boiling point is going to be beryllium chloride because it has the stronger intermolecular attractions. The stronger dispersion forces means higher boiling point. Okay. Next one. PF3 or BF3. Okay, so phosphorus is 5 plus 3 times 7, so that's 20, so that's 26 total. Boron is 3 plus 3 times 7, so this is going to be 24. All right, so with phosphorus, that's 24, and it has a lone pair. So that's 26. Okay, so right away, the lone pair means that we have a shape that is asymmetrical, and that's going to be polar. And specifically, it's going to be dipole. BE or BF3. Boron is the other example that cannot have a full octet. It's only going to have 3 bonds. So because there's no lone pair, it's got 3 bonds, all equally spaced out. This is trigonoplanar, this is nonpolar, and this is dispersion. So PF3, which is polar and has dispersion forces, is stronger attractions than BF3, which only has dispersion forces. So it's going to, PF3 is going to have the higher boiling point. Okay, let's try the next one. C2H6. All right, so we've got 8 plus 6, so 14. And then CH3OH, so that's 4 plus 3 plus 6 plus 1. So that's also 14, okay? So C2, the carbons have to be in the center. You guys remember that? The H's cannot be in the center. I should have 7 bonds, and I do. So that's the shape of C2H6. Polar or nonpolar? Nonpolar. Nonpolar means it only has dispersion forces, okay? All right, CH3OH. So C and the O would be here. That's an H. So if we count 2, 4, 6, 8, 10, 12, 14, there are my 14 electrons. What type of intermolecular attraction does CH3OH have? Yeah, it's got H bonding. It's polar, and it has H directly attracted to O. All right, no contest. CH3OH has the higher boiling point. You guys see how we're going about doing this? All right, so we are reaching back to the beginning of this unit when we drew Lewis diagrams. We're assessing the shape and the polarity because the polarity will tell us what type of intermolecular attraction it has. Whether it's dispersion, if it's nonpolar, or if it is polar, that means it has dipole-dipole, or if it has hydrogen bonding. Okay? All right. MgCl2 or HBr. So here we have a metal and a nonmetal. This is ionic. A metal and a nonmetal. Remember, in ionic substances, you have positive ions next to negative ions. Okay, and HBr is a simple small molecule. It's polar, which means it has dipole, but ionic is way stronger of an attraction than dipole attractions. It's not even close. So, no contest. SiBr4 or MgCl2. So 32 electrons for that one. And oh look, metal, non-metal. This is ionic. I don't even have to finish drawing these out. Ionic wins. Because SiBr4, if I did draw it out, would end up being non-polar because it's tetrahedral with the same atoms in all directions. And it's non-polar. If it's non-polar, that means only dispersion forces. Ionic attractions are far stronger than dispersion forces. Okay. So this next one, C5H12. Okay, so we drew this on the board yesterday for you during the lab. If you recall, pentane, 5 carbons in a line, and H's above, below, and on the sides. And that's how we get our 12 H's. And we had said then that this had what type of attractive forces? Yeah, it's nonpolar. It's nonpolar, so it only has dispersion forces. Okay. So if we compare that with this other formula, C4, where there's 4 carbons in a line, and the last atom is going to be a fluorine. And we have H's. This time we only have 9 H's, which makes sense because if we count up the places where they can be, there's only 9 places. All right. What type of... Is this second molecule, or is this polar or nonpolar? It's polar. Which means it's dipole. Dipole, dipole. So dipole, dipole versus dispersion forces. Now, if we were to add up the electrons, the electron count would be very similar. But the simple fact that they both have similar numbers of electrons, but one of them is polar, one of them is not, means that this is going to have the stronger attractive forces, and higher boiling point. Is this starting to make more sense? Okay. So you have to know molecular shape, you have to know if it's polar, you have to know which intermolecular attraction, and then you're going to kind of use this ranking here in terms of strength. Again, knowing that ionic and metallic kind of slide back and forth with each other, but other than that, the order is true. Okay. So then, SiO2 or SiCl4. I'm going to tell you right now that I don't need to draw anything for this. Why is that? Why is that? Yeah, Kristen. Yes. SiO2 is network covalent. And network covalent has the strongest attractions out of anything, which means it has the highest melting point out of anything. So let's review what the network covalent combinations are. It could be either silicon by itself, carbon by itself, silicon dioxide, which is what this is. This has another name. It's called quartz. Or any combination of these guys. Any two of those together is going to be a network covalent. And you should recognize them as being the strongest attractive force and thus the highest melting and the hardest. So SiW or BC or SiC or WB, okay, and so on. SiCl4, if we did draw it, this is going to end up being tetrahedral and nonpolar. Right, if you did draw it, but if you can recognize something as being network covalent, you can just state that it is network covalent, and you don't really need to draw the rest. Yeah, Ben.
So because SiCl4 has chlorine, it's not network covalent?
Right. It's bonded with chlorine in such a way that it makes a tetrahedral molecule. It's not as interconnected as like diamond is. Okay. All right. So that is how you compare and tell me which one has the higher melting or boiling point. Now, notice that I said melting or boiling. right? If the two substances are gases or liquids, then we will use the term boiling point. But if the two substances are solids, then I will use the term melting point. You don't have to differentiate that, right? The way you figure out the answer is still the same, regardless of whether I'm asking about melting or boiling. Okay? You're still looking for whichever one is stronger. Okay. All right, let's talk specifically about evaporation. I know we did the lab yesterday, but maybe this will help clear up what happened. So, first, evaporation is the process of liquid becoming gas. Okay? In any liquid, anytime you have a liquid, there will be some evaporation. Anytime. If a liquid is present, there's evaporation taking place. So here's liquid A, and these little arrows represent how much evaporation is happening. Right? And then here's another liquid. We'll call it liquid B. And there's more evaporation happening. When you have different liquids, if there's more evaporation happening, it's because the molecules are not holding on to each other as strongly, which means they have weaker intermolecular forces. That's why they're able to leave. So, an example, nail polish remover, right? If you've ever used nail polish remover, and if you've ever spilled any, like on a countertop, you don't even really have time to wipe it up. It evaporates so quickly, by the time you turn around, get yourself a paper towel, come back, it's already gone. Right? It evaporates that quickly. Water, on the other hand, water will hang around because water has really strong attractions. Water has hydrogen bonding. Okay, so it takes, water will evaporate, but water just takes a long time because its attractions are so strong. Okay. So, another term I want to bring up is called vapor pressure, which I don't think is in here, so we're going to add it in here. I'm going to add a page. So vapor pressure is a measure of how much evaporation is taking place. So going back to that same example of liquid A and liquid B, because there is evaporation, that means liquid molecules turn into gas molecules. So between these two examples, we're going to have higher vapor pressure above liquid B because there's more evaporation taking place. And above liquid A, you're going to have lower vapor pressure. So if you can tell me which one evaporates more, i.e. which one has weaker attractions, you can also tell me which one has higher vapor pressure. Okay? So let's try that. Let me give you a couple of liquids here. Using some liquids that we had in lab. We used these two in your lab yesterday. If we diagram them out, here is the first one, and again, here is the second. Which one of these two will have a higher vapor pressure? Taylor?
C5H12.
Yes. And what did you base your decision on?
There's weaker
Okay. This is nonpolar. It has only dispersion forces. This has H bonding as well as dispersion forces. So weaker intermolecular attraction means more evaporation, which means higher vapor pressure. It also means lower boiling point. That has a lower boiling point because this one has the higher boiling point. So what is the relationship between vapor pressure and strength of IMAs? So opposite. If one goes up, the other one goes down, right? So vapor pressure is inversely related to intermolecular attractions. The stronger the molecules are attracted to each other, the less vapor there will be. Does this term make sense? Vapor pressure? Okay. All right. So, what things affect the rate of evaporation? So, there are things that you can do to speed up evaporation or slow evaporation down. Okay, so the first one is surface area. So what you need to understand about evaporation is that only molecules at the surface can escape. So I'm going to use the space above here and draw you a picture. If we have a beaker of water, that beaker of water obviously is filled with, water molecule is filling the cup throughout, or the beaker throughout, but only the molecules at the top are the ones that can leave. Because if it's not at the top, if it moves, it's not really leaving. So only molecules that are at the top can evaporate. Now let's compare that. Let's say that this is 100 milliliters of water. Okay? But let's compare that with a spill. All right, so somebody knocks over their beaker. It all spills out. It's the same amount of liquid. There's 100 milliliters here. But by spilling it, you now make a greater proportion of that water available to the air. Your surface area has increased. And when you increase the surface area, you increase the rate of evaporation. Again, it's the same amount of liquid, right? So you ever take a towel out of the dryer and it's still wet? Right? If you jam too many clothes into your dryer, it all is crumpled and it's harder to get that stuff to dry. Right? But if you have fewer stuff in there, then they can kind of spread out more and there's more surface area for the molecules to leave, the water to leave. It's also the same idea as putting something on a clothesline. Right? By hanging it flat, just letting it dries faster than if it were like balled up in the corner of your room underneath your backpack and other stuff. Okay. That makes sense? Surface area? Okay. Temperature. An increase in temperature increases the average kinetic energy, therefore increasing the amount of molecules with escape velocity. Okay, that's a mouthful. Let me explain what that means. First of all, let's define temperature again. I know we did this in Unit 1. Oops. So temperature is defined as average kinetic energy. When you take the temperature of something, you're getting a reading of the average, but it's understood that there are molecules that are faster and slower. Okay? So, in any sample, I'm going to skip down to this picture here. In any sample, this graph right here is a sample of a liquid. And on the y-axis is the proportion of molecules or fraction of molecules. We'll use fraction because that's... On the x-axis is kinetic energy. And this dashed line represents where the average would be. Okay? But in any distribution, you understand there's some that have more energy, some that have less. Okay. So this shaded area right here, this is the minimum energy that's needed for evaporation. So by looking at this graph, what that tells you is that of the entire sample of a liquid, roughly 10% of that sample can evaporate. I'm estimating here, but do you see that? Roughly 10%? Okay. Okay, so only the particles with high kinetic energy can escape or evaporate. All right, so if only the fastest moving molecules can evaporate, when they do evaporate, the graph looks like that. Does that make sense? These guys here, the ones that could evaporate, they did, and they left. So if the fastest moving molecules have evaporated and left, what does that do to the average energy of the sample now?
Decreasing.
Yeah, less. The average kinetic energy is going to lower, it's going to shift. The original average is going to go down. It's just like if I said, you take your 4 best hitters off of your baseball team because they go on the quarantine list. What is the average batting average of the remaining team members? It's less because you took your 4 best hitters that if they were gone, then it's going to change. Okay, and that is why evaporation has a cooling effect. That is why when evaporation takes place, the temperature goes down. Because the molecules that have enough energy to leave, they do leave. And that means the remaining energy is less than when you started with. So in every single instance in your lab, the temperature started going down as soon as you lifted those filter papers out of the bottle. Okay? Okay. So what effect does that have on the temperature? Well, of course, it's going to lower it. If we look at a picture of all the water molecules present in a sample, the high energy molecules are the ones leaving. Medium energy, they might make it to the top, but they get pulled back down. Lower energy, they don't really move too much. So I hope that picture makes sense. In order to evaporate, They need a lot of energy because think of it as they have to break away from each other. They have to break away from their neighbors. Water molecules, when they separate from each other, what are they breaking? If molecules are going to completely pull apart from one each other, what are they breaking? Yeah, hydrogen bonds, specifically, right? Intermolecular attractions is what they're breaking. And we know that intermolecular hydrogen bonds are strong, so it's hard to break them. Okay. Second graph. Here we have a liquid, and its temperature is taken at two different temperatures, temperature 1, temperature 2. So the axis on the y is still the fraction of molecules. On the x is still kinetic energy. And this line here still represents the minimum energy to evaporate. But notice that if one of the temperatures is higher, T2 is a higher temperature than T1, look what happened to its distribution. You see how its curve changed? When you increase the temperature, the curve shifts, and the curve that shifts means there's a greater proportion of molecules that can evaporate compared to before when it was cooler. And so the point of this, at a higher temperature, you increase the fraction of molecules that can evaporate. And that's what you should be taking away from this graph. Let me ask you a question. What if I cooled it down? What if I drew a third line on this graph that was a colder temperature than both of these? Yeah. So if I have a cooler temperature, does that make sense? Look at the small amount of molecules that can evaporate now if I lower the temperature. What if I added a third temperature here where I heated it up even more? All right, so if I just kind of get it near boiling, look how the curve changes. And now you have even more of the sample that can evaporate. So this is how temperature changes the rate of evaporation. The hotter it is, the more molecules that can evaporate. Okay? Based on this energy distribution. Okay. Let's look at another similar looking graph. But here we're comparing one picture that has hydrogen bonding and one that only has London forces. These two are at the same temperature. These are two different substances at the same temperature, but notice how the energy needed to evaporate is at different places for these two. First of all, which one of these is it more difficult to evaporate? The top or the bottom graph? The top. The top one's more difficult because the top has hydrogen bonding, which is a stronger intermolecular attraction, right? Which means molecules are more difficult to separate, which means less evaporation. The weaker it is, then the more molecules can evaporate, greater evaporation. Which one of these has higher vapor pressure? The top or the bottom? The bottom. Weaker attractions, more evaporation, greater vapor pressure. Okay, so let's bring this full circle now. I'm going to give you a couple of formulas, and I'm going to ask you some questions about them. All right, and I want you to see if you can answer them now based on what we just talked about. Okay, so what do we think? Yes. No, sorry, no. That's not HF, actually. It's actually going to be fluorine has the higher vapor pressure. Why would that be? Why would that be? Nate?
HF has a greater IMA.
It does. What is it?
It's dicodyl.
Keep going.
It's hydrogen.
It's hydrogen bonding, yeah. It has hydrogen bonding, which is stronger than, what does F2 have? London, right. So that means H bonding, which is stronger, intermolecular attractions, which means less evaporating, which means lower vapor pressure. Okay, let's try another one. You should remember C4H9OH as butanol. We used that in our lab yesterday. That's the one where the temperature changed the least out of all the chemicals you tested. I believe it only changed about 2 or 3 degrees. Casper.
CaCl2.
Yes, it is. Why?
It's ionic, so it has it's like stronger than H bond.
Yes. Definitely. Here's a tip. All ionic compounds are solids. Think about that. They're all solids. All ionic compounds are solids. What you used yesterday in lab was either dispersion forces or hydrogen bonding. What state of matter did you use in your lab yesterday? Liquids. Okay. Let's try another one. Ben?
C4H10,
Why do you say that?
because it has dispersion
okay, it's nonpolar with only dispersion forces, right? Well, what's going on with the other one? What does it have? Yeah,
Hydrogen bonding.
has H bonding. Okay, so we've established what they have. So tell me, why does C4H10 have a lower boiling point? You're right, but why? What specifically about it? It's a simple statement. Don't overthink it.
Because it's weaker than hydrogen bonding.
Yeah. Dispersion forces are weaker than hydrogen bonding, right? Weaker intermolecular attraction, lower boiling point. Okay. All right, let's do one more. Which of these has the higher melting points? Okay. We talked a little bit about these guys a while ago. Can someone tell me what you know about a formula like this? And yeah, Kristen?
Sugar.
How'd you know it's a sugar? Okay, so carbon hydrogen oxygens. And the oxygens should be about the same number as the carbons. Okay, so that's a sugar. And the thing about sugars is they have lots of hydrogen bonding. All right, what state of matter is table sugar? Solids. C5H11OH we didn't use in the lab, but we could have, and if we did, it would have behaved just like butanol. It's a liquid, right? So sugars have the higher melting point. How are we doing? Hopefully we're doing a lot better than we were 50 minutes ago. Okay. All right, so we are done with the notes.